colloidal quantum materials, such as quantum dots dispersed in fluids, exhibit unique quantum behaviors thanks to their small sizes and tunable properties. When these materials are exposed to external magnetic and electric fields at ambient temperature, researchers have found that quantum effects can be induced or enhanced in ways that are both surprising and promising for practical applications. For example, applying an electric field can lead to phenomena such as the Stark effect, where the energy levels within the quantum dots shift. This change can modify the emission wavelength and other optical properties, effectively allowing us to tune the quantum behavior of the material. Could such tuning pave the way for next-generation displays or optical sensors? Many studies suggest that by carefully controlling the electric field, one can design devices with highly controllable optical responses at room temperature. External magnetic fields, on the other hand, can introduce effects like Zeeman splitting, where the magnetic field causes energy levels to split based on electron spin states. In a colloidal solution, this can lead to spin-dependent behavior, which is particularly exciting for quantum computing and spintronics. How does this help? By manipulating the spins of electrons in quantum materials, it may be possible to encode and process information in novel ways that are not available with conventional electronics. Moreover, combining both electric and magnetic fields can produce even more complex quantum effects. For instance, the interplay between these fields can enhance electron confinement or lead to phenomena such as magneto-optical modulation. In practical terms, researchers are exploring how these induced effects can be used to improve the efficiency of energy conversion devices, create highly sensitive sensors, or even drive new catalytic processes. One promising application is the development of fluid-based devices where the quantum properties of the colloidal particles can be dynamically controlled in real time, offering a platform for adaptive and reconfigurable technology. Critical evaluations of these methods involve rigorous control over experimental conditions, such as ensuring that the fields are applied uniformly and that the fluid medium does not introduce unwanted interactions. Researchers use advanced spectroscopic techniques and electron microscopy to monitor changes in the quantum states of the colloidal particles. These measurements are crucial for determining how effectively the external fields induce the desired quantum effects and whether these effects are stable under ambient conditions. Could these strategies revolutionize how we design quantum devices? The ongoing research indicates that by applying external fields to colloidal quantum materials in fluids, we can achieve remarkable control over quantum properties without needing extreme conditions like ultra-low temperatures. This not only challenges conventional wisdom, but also opens the door to practical ambient temperature quantum devices for applications in computing, sensing, and energy. Applying an external electric field to colloidal quantum dots modifies their energy band structure by shifting electron and hole states through the quantum-confined Stark effect, QCSE. This field-induced shift reduces or increases the band gap, affecting the optical absorption and emission properties of quantum dots suspended in a fluid. Strong fields can even induce dipole moments, leading to quantum dot alignment and collective optical effects. This allows precise tuning of fluorescence and charge carrier dynamics in quantum materials at room temperature. For example, in CDCE, quantum dots applying an electric field shifts the emitted photon wavelength, causing a color change in their luminescence. It's like tilting a glass of water, making the light refract differently based on the angle, changing the appearance of the liquid. When a magnetic field is applied to quantum dots, it lifts the degeneracy of electronic energy levels, a phenomenon known as Zeeman splitting. This allows for the generation of spin-polarized states, which are crucial for quantum computing and spintronic applications. In fluids, suspended quantum dots align their spins along the external magnetic field, altering their optical and electronic properties. These effects enable non-thermal control of photoluminescence and charge carrier behavior in solution. For example, magnetically doped quantum dots, such as nin-dope CDTE, show distinct photoluminescence shifts when subjected to magnetic fields. It's like aligning tiny compass needles in a fluid, where the external magnet forces them to face a specific direction. Electric fields can modulate charge transport in colloidal quantum materials by shifting electron wave functions and inducing field-assisted quantum tunneling. This allows researchers to control mobility, conductivity, and charge recombination rates without changing the fluid temperature. By carefully adjusting the electric field, it is possible to regulate carrier injection in quantum materials, influencing their optoelectronic behavior. Such effects are useful for nanoelectronic and quantum sensor applications. For example, quantum dots in electrolytes exhibit field-dependent photoconductivity, which can be tuned for optoelectronic switches. It's like pushing charged dust particles in water with a static electric field, altering their motion without direct contact. Two-dimensional colloidal quantum wells and graphene-like nanoflakes exhibit the quantum Hall effect, QH, when subjected to strong magnetic fields in solution. The applied field quantizes the electron motion into discrete Landau levels, affecting conductivity and optical responses. Unlike in solid-state systems, quantum materials in fluids retain dynamic reconfiguration properties, making them useful for tunable nanofibers. These effects have potential applications in magneto-optoelectronic sensors and energy storage materials. For example, solution-processed MOS2 nanoflakes demonstrate magnetic field-dependent conductivity changes in liquid-based transistors. It's like controlling the movement of bubbles in a magnetic liquid, restricting their positions to specific levels. Colloidal plasmonic nanoparticles, such as gold and silver nanorods, exhibit shifts in their surface plasmon resonance, SPR, when subjected to external electric and magnetic fields. This occurs because applied fields influence the collective electron oscillations, altering light absorption and scattering. The ability to dynamically tune SPR in liquids enables applications in real-time, biosensing, tunable filters, and optoelectronics. These field-induced effects provide a method for remote non-contact tuning of optical properties in nanofluids. For example, electric field-induced plasmon shifts in gold nanorods are used for tunable photonic circuits. It's like changing the pitch of a guitar string by pressing on it without plucking. The resonance shifts without direct excitation. External electric or magnetic fields drive self-assembly of colloidal nanoparticles, forming controlled structures with emergent quantum properties. These fields induce dipole interactions and alignment, enabling dynamic reconfiguration of quantum dots, nanorods, or 2D nanoflakes. Field-induced self-assembly allows for the creation of adaptive nanostructures for quantum optics and energy storage applications. These effects can be reversed or dynamically tuned, offering a pathway for programmable quantum nanomaterials. For example, electric field-assisted assembly of perovskite quantum dots is used to create high-efficiency optoelectronic devices. It's like aligning iron filings in a magnetic field, where external control dictates the formation of structured patterns. The optical Stark effect occurs when a strong external field induces virtual electronic transitions, shifting energy levels without direct excitation. This allows for non-thermal control of electronic and optical properties in quantum fluids. It is useful for ultra-fast modulation of optical signals, optical switches, and non-destructive quantum state preparation. This effect is particularly beneficial for quantum computing and high-speed photonics applications. For example, optically driven quantum dots exhibit coherent exciton manipulation using external electromagnetic pulses. It's like pulling on a rubber band without letting go, stretching its energy state without permanent deformation. Quantum decoherence, the loss of quantum superposition, can be controlled by external fields influencing how long quantum states remain coherent in liquid environments. Applying magnetic fields to electron or hole spins in quantum dots can extend or suppress decoherence times, enabling long-lived quantum effects at ambient temperature. This technique is essential for quantum information storage and spintronics applications in solution-processed materials. Understanding field-controlled decoherence could pave the way for room-temperature quantum devices. For example, magnetically doped colloidal quantum dots have been engineered to exhibit longer spin coherence times crucial for quantum computing. It's like freezing a soap bubble in place with a magnetic force, preventing it from popping too soon. Combining electric and magnetic field control over quantum materials in liquids allows for the design of dynamic, reconfigurable quantum fluidic devices. These systems could enable real-time quantum sensors, tunable nano-optoelectronic devices, and programmable quantum interfaces. By integrating multi-field effects, it becomes possible to control quantum interactions, energy transfer, and self-organizing behaviors in solution. These approaches lay the foundation for quantum fluidics as a next-generation technology. For example, hybrid magneto-electric quantum dots are being explored for liquid-based quantum transistors and memory devices. It's like controlling ink dispersion in water using electric and magnetic forces, forming complex patterns that change dynamically.